And I just wanted to say thank you guys for all your support during the chaos of that week. I know there were some kind of changes in schedule that we were faced with, and some kind of unexpected requests from the AMO team that you guys very graciously agreed to. And also as a result, we had some really interesting requests to print with Scalmalloy, which we did not anticipate. So it was quite interesting. I don't think our 10 kilograms of Scalmalloy will allow for that, but at least it was a good follow up from everyone that was on the line. How did you find the experience, John?
Yeah, no, I think it worked out because I think the level of engagement sort of made sense, which was Kevin and I were kind of supporting you from a distance. And I think our job was to kind of help put it in context, but I was really impressed with the parameter piece. I mean, I think Kevin and I both said it, having not ever even had the material in your possession before, to being able to, print good quality stuff was pretty impressive. People try. It is a more tolerant, it's a forgiving material, I think, in some respects, but yeah, I think the science component of it, I think, prevailed.
Yeah, and one of the interesting aspects is that you can do a lot of work outside of the lab to be able to estimate what you think may work and why things may go wrong. So at least probing the space and validating that through a short build was what Sagar had done. So he basically was able to hypothesize where the process parameter space would break down and give us bad parts, as well as predict a process window where we thought the parameter space was going to give us successful parts. And by just very quickly validating that, you're able to work backwards and retune some of your material parameters, actually, to be able to calibrate your model and build with a higher confidence within the process window as a second try. So I think that's what Sagar had done, and hopefully we'll be able to review some of the results that he was able to gather.
This is Kevin. I want to say once again how impressive your advert was, because having gone from nowhere. Because I mean, what it really shows is that even if you have a robust alloy, that there's lots of ways you can get last confusion. There's lots of ways you can get keyholing, and you were able to dial those in very quickly. And before we had our first call, the idea was we're going to use, we got lots of experience with 10 silicon, which unfortunately is half as strong as the target. And so, as soon as we said you needed to be twice as strong, here's one of the two alloys. You found them and figured out what had to be done to successfully make those, and using your method to be able to go from one type of alloy to one that is significantly different in composition and melting characteristics.
Well, that was half the fun, was finding the material, and the other half tuning for the material. So I don't know, Sagar, if you have some updates on the technical side.
Yes, I can share my screen now and have the presentation going. So I do have some updates on the X-ray CT scans of the best samples that we had, and also I analyzed I basically analyzed all the 3 samples that we went through to achieve the parameters that we use for the competition. And here, I mean, I summarized it for other purposes, but essentially we ended up using a bit of all of these, right, for our process parameter development. One is the processing diagrams that we've developed, and secondly on the microscale simulations, which is predicting the melt pool depths on descent. And the beam path planning is just about deciding what do I use for the side skin surfaces, what do I use for the down skin surfaces, and so forth. We did not use high-speed imaging for this, but we used X-ray, XCT scans, and metallography is what we are doing now, although we didn't use it for the competition. And then Yeah, for the competition, I think we just use surface topography again through CT scan data sets. We try to understand that. And yeah, sorry, yeah, I had summarized this for another purpose again, but this is all the alloys that we worked with. And in my own PhD, I've worked with ELSI 10mg in quite detail, and Ti64, which was initially supposed to be part of my PhD, but aluminum was just interesting to work with. And now we are working with a new near alpha Ti6242 alloy, which has its unique issues. And yeah, so that some cracking in another sense, like it's cracking perpendicular to the build direction, which we are trying to figure out now on that material. So that's unique because it's generally along the build direction if it's like due to the delta T. Like for 7 series alloys, I'd expect it to be along the build direction or so. But this is unique that we are working on, and so
And
yeah,
I
now
should mention, Sagar is trying to figure out why some of our parts did not crack, which is the puzzling piece that we're trying to figure out, which is
yeah. Because we did have certain regions in the processing diagrams, like especially in the conduction mode areas, which did not crack. And we have certain hypotheses, but like maybe there was alloying element losses. That's a reason, because it doesn't seem like residual stresses again, because we didn't have cracks close to the build plate. It was like about 20 millimeters after building where we got cracks. Yeah, we're trying to understand that. But for Scalmalloy, I think what we initially had done is we had a process parameter set called by sample code A, which was pretty good for aluminum, and we had expected it to give us certain issues with Scalmalloy because of the different thermal conductivity and as well as density and specific heat. Those are the values that we got from the AP Works data sheets. So when we use the parameters directly from ALSI 10mg to Scalmalloy, we obtain something like quite a few lack of fusion pores. Like, so I've colored the pores on irregular pores as aspect ratios below 0.7. That's commonly used in literature or a few papers that I read. So we got quite a few lack of fusion pores in this sample, and which led to like a reduction in density of about 0.1%. And then in this particular set of processing parameters, we were again working with a defocused beam, and the main goal was to avoid this surface vaporization threshold. So this, I must mention that as part of the paper that I've cited here that we developed, um, the two things we try to consider in that paper is not only that we need to figure out this vaporization threshold, but also that for different alloys, um, it does work differently in the sense that for aluminum alloys, we classify that material in this paper as a completely different set of alloys, as a high reflectivity and high thermal conductivity alloys, where we propose for the first time, I think, in that work that surface vaporization is a much bigger issue in aluminum alloys compared to titanium alloys for the purposes of that paper. So the same threshold would not apply for titanium alloys. We would rather be okay with about vaporizing up to 0.5 times the beam spot radius. So those are the dimensionless variables that we created. And for titanium alloys, for nickel-based alloys, and for ferrous alloys, we proposed those thresholds. But for aluminum alloys, we propose the surface vaporization threshold. Uh, and so as soon as I tried to go to this sample code B, which was very close to the surface vaporization threshold, and it was predicted to be above, so I did end up with, like, so we did end up with a, a lot of near spherical pores, as we see here. And most of these pores do seem to be originating due to the keyhole mode defects, and as we would have expected. And we also noticed that these pores are much larger than you would actually observe in materials such as titanium, and so wherein um, slightly deeper melt pools are still stable in the other alloys, but for aluminum, it's it's it is not impossible that you can obtain good processing parameter sets even in these regions, but that would require more complex simulations of us understanding everything that happens in the keyhole mode and including the laser ray tracing. Like you have the ray tracing to be included in the algorithm to account for those defect predictions. But then what I then went with for sample C, which was our best parameter set, I actually ended up defocusing the beam even more. The reason I had to do that is the sample B was already at 400 watts. So it was at the physical limitation of the machine. And so there was no way that I could really go further in while obtaining the melt pool depth to have avoid lack of fusion. So then I went with sample C, wherein I defocused it to a zone of about the beam spot diameter we used was close to 180 microns. So it was about 80 microns more than sample A and sample B, which was at about 100 microns. But the temperature prediction model from the same paper, at least that we were predicting us to actually obtain higher melt pool depths with this processing parameter. And the melt pool depths predicted was close to 2 times the powder layer thickness. So we wanted to stick with that because that's a general recommendation in literature that you end up avoiding most lack of fusion pores, at least with these melt pool depths. And in this sample, as we see that we have much lesser pores than either of the samples. And even the pores that we have actually are concentrated towards the edges of the samples. And that's for another reason, because we had to do a trade-off of whether we want a good surface roughness or no surface pores. So we went with the trade-off of having very good surface roughnesses. And the reason I will explain in a bit. But yeah, we also actually managed to scan like the expanse artifacts. I think, yeah, so from what I saw, that is this region was a hollow region where we just have collected powder. And like, so collected powder, it was difficult for me to threshold it separately. I'll have to work further on how do I threshold like raw powder, because this everything in this thin region is just, it was unmelted powder, sorry, yeah, unmelted powder in that artifact. But I think we did get all of the, we say, all of the features printed. But yes, at the very, what do you say, because this is a very small sample, right? So this has a width of about 14 millimeters and a length of about 11 millimeters. So at that scale, I think we can definitely further improve our side skin surfaces and down skin. So that's what we have to work on. And that is the part of the remainder of my PhD, still trying to figure out how to predict why we get certain parameter sets roughnesses which are much better than the others, because that's not been researched much in literature. Like studying side skin surface roughnesses we came across almost no paper trying to predict it, at least until now. And here I just try to also similarly threshold the pores. But so here we see, of course, a lot of pores. That's because this was the pores in between the powder particles. So at the top, of course, there was no powder in this region, because some of it settled down because of gravity later. So we had some gaps. And all of these pores are in between the powder particles, actually. That's how I thresholded them. I could look into, sorry, yeah.
What's the resolvable pore that you can get to with this scan?
Oh, yes. So with this scan, since we scanned it in a single scan, we had a voxel size of 15 microns. So which means, okay, as long as a pore had an edge length of 45 microns, like minimum dimension, then we could resolve it. So pores below 45 microns were not resolvable by this scan that we did.
Okay.
So these are all about 45 microns at least edge length. And I have a few slides on the side skin surface roughness. I think a few of which we had discussed before. So the way we had, so on this, since we didn't have any literature to look into, we had gone into designing experiments for Ti64 using some conduction mode melt pools, as well as some melt pools which are pretty deep into transition mode or keyhole mode. And we observed a trend consistently with replicates wherein we had surfaces with much lesser effects of uh, adhered powder particles. So we were taking advantage of the powder denudation. So although excessive vaporization is not good for melt pool stability, it ends up being pretty good for denuding powder next to the melt pools. So since your side skins is a single scan, if we have just the scan on the side skin surfaces to be in the transition mode, we can achieve much better surface finishes. And I think this is what we had seen once before in our presentations, that when we used, when we translated these findings, okay, yeah, my slide title is incorrect. This is Scalmalloy. So these were our side skin surface finishes from Scalmalloy. And compared to when we use a conduction mode melt pool on the side skin surfaces, we do observe differences in there. And we were able to get some better like surface roughness images and data sets out of these papers, out of those samples. So we printed cubes. What we did in those cubes is we had the core, like the core of the cube, to be the processing parameters that were that were our ideal that we submitted to the competition. But and then one of the cubes, what I did is I used uh, the same defocused beam conduction mode processing parameters to be on the side skin surfaces, wherein, and these are the four sides of the cube. So
That's
we
pretty
just took,
bad.
yeah, that we took one images from each end. And this is, yeah, in these surface roughnesses are much worse than Ti64 as well, which to an extent is due to just aluminum alloys always give us worse surface roughnesses compared to titanium alloys. And this is again of interest to me to understand why, like why with titanium, no matter what processing parameter sets I use, with the side skin surface finishes, I never really go above 25 microns in SA,
Hmm.
but here I can go to as high as 45 microns. But then when I use transition mode, I am able to go to as low as 15 microns in certain surfaces. And in one edge of the cube, we had slightly more, up to 30 microns. But in most cases, the effects of adhered powder particles are minimal. And I think these blobs that we see, I think are more due to liquid metal spatter than potentially adhered powder particles. So this is again because this was this was the first shot. Like we took only one shot at this material, and that's all. This is what we submitted for the competition. But I think it's more like the more I understand why do we have these effects, and how do I also control the liquid metal spatter, I think that's when we will able to get almost all of the side skin surfaces to just have the melt pool signatures, but not adhered powders or the liquid metal spatters show up in our data sets. Yeah, I think, yeah, that's all I have updates for now that I could do.
Yeah, so the idea is how do we, the first question that was posed to Sagar as part of his research program was how do we leverage low-cost models to be able to predict process windows for a diverse range of materials without having to run costly simulations as well as costly experimental runs. And I think for optimization of process parameters in the core, that was essentially the modeling theory that was developed was stress tested against a lot of different materials. And now the challenge is how do we obtain proper surface quality as well? And how do we construct models that can predict process windows for good surface quality, which now you add complexity in terms of the spatial orientation of your surface. Which Sagar has only studied in depth the side skin, which is the vertical surface and top surface. But then how do you extrapolate your modeling theory to encompass more complex surfaces as well? So that's where we are with that study. I don't know where the tensile work is or where the tensile samples are.
The tensile samples, I think, yeah. So just today, I think, yeah, today I got an update from the machine shop that they begin machining, and I think I'm going to read out what the machinist told me. So Carl told me that I think he's going to polish. He was able to successfully machine the gauge length and even the curves, but he had to take out about 200 microns on the surfaces to keep the curvature. And for what he's going to do for the grip sections is he's just going to like kind of sand it off or polish it himself. But yeah, I think he's able to do that. That's it. And I don't know, the machinist recommended to also have a light polish of the gauge length, as this will change the original properties uh, because of clamping and turning a delicate part on a CNC. Yeah, I don't know if we need to do that. I think the machining finish should likely be good. Yeah.
Yeah, as long as he doesn't damage the grip, the gauge section while he's finishing the grip sections, we should be fine. Yeah.
Yeah.
Yeah. Well, thank you so much, Sagar. I don't know if you guys have any other comments, but we're really excited to wrap this as for the scientific community and see how we can move forward, because we had some interest as well in printing Scalmalloy now for some interesting applications as a result of the AMO. So I think this created a lot of interest, and we learned quite a lot from it.
I did have one question earlier on when you talked about the surface roughness being higher for aluminum and better on titanium. Do you attribute a lot of that to the higher surface tension of aluminum? And it's not wanting to flow and wet like aluminum, of titanium, not wanting to flow and wet like aluminum does.
Oh yes, and now that when we saw those images of the surfaces, we did have more melt pool. Like we could see those melt pool spatter signatures as well on the Scalmalloy samples compared to the Ti-64 samples. Like in the Ti-64, when we had in the transition mode, we still had a bit of adhered powder particles, but almost no signatures from melt pool spatters on those surfaces. But yes, yeah.
Yeah, it's a more turbulent process, it appears. Yeah.
So Scalmalloy is a more turbulent process? Or?
Yeah, it just appears in the process zone, compared to some of our other alloys.
And what is how about the characteristic of the powder? Because, I've not looked at Scalmalloy previously, but I've looked at a variety of aluminum silicon 10 powders, and they're, I would say, on the whole, more potato-y than, let's say, a titanium. So it could impact their flow and then stacking behavior.
Yes, and that is even the powder size distributions actually. For the Ti-64, we have like plasma atomized powders, but the powder size distribution, the range is 15 to 45 microns, whereas for common ALS at NMG as well as our Scalmalloy samples, like the powder size distribution was 20 to 63. So that itself will have a huge impact on. I mean, that will potentially have an even bigger impact than just the processing parameters on what we get as a final outcome, because any other powder particles with these higher dimensions will add much more.
Yeah, because it does seem to me that you have to, one is by controlling the spatter, you remove the things that are flying around that can smack into the side of your mouth, which will immediately reduce the surface roughness. And that's a characteristic of a lot of additive techniques. But I think spatter in general is not characteristic of a process under control. But in the additive world, we love to look at it because it makes for good video.
Yeah, and also we were reliant quite a bit for titanium on the concept of we were almost enforcing or hoping for powder denudation around the perimeter of the part. Whereas with a much larger powder size distribution at that scale, that may be a challenge, right? Having powders migrate into the melt pool and create that denudation zone, which that's something to look at as well. And we may use high-speed cameras, Sagar, to look at that if we have the opportunity to set up the experiment. Yeah.
We kind of have some interesting bookends there from something that's very spherical coming out of plasma, which then characteristically is going to have better flow and presumably spread, but then it also will be impacted by the melt zone itself. So the energy if it takes little energy to get into position, it takes little energy to get back out of position.
Yeah, that's correct. Yeah. Well, that's quite interesting. All right. So I would say we'll continue to exchange some of the results that Sagar is going to obtain. We now have the benefit of another team member joining us, a new postdoc that can help us look at the sample characterization, so that Sagar can now focus back on modeling theory. So starting next week, we'll have the benefit of the postdoc joining us to be able to look more in depth at the microstructure or any other aspects of the material that we may not have the bandwidth to do through Sagar. So I'm really excited to see what we're going to find. And if you have any suggestions as to what to look for in the microstructure, if we're going to open these samples up, we'll be mindful of that. If not, we'll do it as an exploratory pathway.
Okay.
Awesome. Okay, well, we don't have any other updates, Sagar. I don't know if you have any other comments, last-minute comments to talk about, but we're really excited to put this all together into a more comprehensive summary that's more digestible by the research community, and hopefully we can actually print some really good parts for whoever's interested.
No, I think other than this, I do have the metallography results as well. I think which Dr. Statry saw before. I have the metallography results for all of those 3 type of samples. I just didn't get the time to add it to the presentation in a good way. But of course, I will be using that to measure the melt pool depths of the given samples from the top layer, because we need that to kind of, validate what we propose from the processing diagrams, that we expected this to be in transition mode, we expected this to be in conduction mode. That's what I'll be validating through that. Yeah.
Awesome.
Also, if you're wanting more powder, I can probably put you in contact with somebody who's got some they're getting rid of, and you may be able to get a really good price on it.
Oh, that would be fantastic. Send us the information, Kevin. That would be great.
Jessica Orr at UDRI. So they've got a bunch of mixed heats. So useless to them, and plus they need room in their cabinets.
Right.
All right. Well, that would be great. If you can share the contact, that would be fantastic.
Okay.
Yeah. Awesome.
Thanks.
Well, thank you so much. John, any last-minute comments?
No. I'm interested to see where this goes next. I mean, one of the things that's bouncing around in my head is if we reduce the requirement to have a smooth surface finish, given that we might machine it, does that allow us to move into a more productive parameter set that we could deposit it, quicker, because the material is a premium. So it would be directly applicable to like a Ti 6.4, but that's probably not today's question. That's
Yeah, so you mean looking at productivity through either changing
Higher
the
layer thickness.
Yeah, layer thickness, beam spot diameter. Yeah, those are all possible. It just restricts a little bit your process zone in terms of, it may restrict your stability zone, but it's highly doable. It could be doable. We just haven't looked at it for this alloy, so it'd be interesting to know, Sagar, if you can translate the recipe for a higher layer thickness. What would that imply in terms of beam spot and power, right? So that would be an interesting conclusion. And if we can do a validation of that, we have the reduced build volume. And if we're printing aluminum short term, we may just translate the recipe that was kind of the most successful one to see if higher productivity is feasible.
Yeah.
Yeah, it's a good question. Awesome. Well,
and there's also some improved affordable surface finishing methods coming out that actually, I'll try to put you in contact with John Mayer on some follow-up on that. Maybe you can print some stuff and they can get some stuff smoothed over there, get those parts smooth, and you can see that effect, right? So I'm much less concerned about layer thickness, roughness now than I was 6 months ago. Well, I think we have a good way of getting rid of it.
Yeah, certainly in aluminum versus Ti, just because it's an easier material to work with.
mm-hmm. No, that's a good point. If you can share the contact or at least make that connection, we know each other, but if the context is correct, I think we'll be able to send some samples out. Awesome. Well, thank you so much, team. Sagar will splice and dice the recording to capture the pieces that were more relevant towards the end.
Yeah,
And I really
think,
appreciate your time.
Yeah, I'm going to send the recording to Miss Rogers and then she'll take care of that.
Thank you so much. It
All
was
right.
nice to see you guys.
Nice seeing all of you.
Bye.
Bye. Take care.